Redgate!
Hello and welcome. Thank you so much for joining my session today, Getting Started with AI and Computer Vision, a guide of obstacles and insights from the field. My name is Kristina Mishra. A quick background about me. I've been a data professional for over 20 years. I've held titles such as data architect, DBA, consultant, developer, manager, coach, and many more. So some of my favorite projects have been working on projects at the CDC, working for CSC for the World Trade Center Health Project, and some global PEPFAR projects. I was a volunteer organizer for SQL Saturday in Atlanta for over 8 years, and for the induction year of SQL Saturday BI in Atlanta. Recently, I went back to school to get my master's in business analytics and studying both the leadership and technical sides of data analytics. And following that, decided I wanted to start getting some certifications under my belt. Start off with a little background about how a 20+ year SQL Server data professional ended up doing computer vision. A few years ago, I took some time to myself and then decided to go back to school and get my master's degree because it turns out that relaxing and doing home projects is not really a good fit for me. I always wanted to go back to school, and I convinced myself it was perfect timing. Never mind that COVID-19 would hit shortly afterwards, and then I would be doing my degree while also teaching my twins for 18 months. After taking a course in the industrial engineering department, I saw a course titled Advanced Analytic Projects. This was a class for a few graduate students to work directly with a company on an analytics project. There were 3 of us, and we had our choice of projects. I can't disclose the exact projects, but they were something like predict performance of an item over multiple years, design a method to suggest optimal locations, and a computer vision project, identify and estimate the percentage of similar objects in an image. I had 0 experience with computer vision, and honestly, I had to Google it. It sounded really cool. Never having let something like experience stand in my way, as a data professional, my entire career has been, hey, can you learn this new thing really fast and implement it? So, of course, my vote went to the computer vision project. Turns out, so did the other 2 students. It was unanimous. And these were really smart industrial engineering grad students. So surely it would be fine. What could go wrong? Turns out, none of us had experience with computer vision, and our collective experience in Python at the time wasn't much better. So somehow we did it. We had to work like mad, but we did it, and we learned a lot along the way. So much that I decided to frame my capstone project along similar lines, because I could take it into new directions and explore things further than we were initially able to do. Again, what could go wrong? And that brings us to this presentation. So this session goes through some of the major things that did go wrong. And hopefully you will have a takeaway from this session that helps you avoid or alleviate some of the pain points that I went through should you decide to embark upon a computer vision project in the future. So before we even get into what went wrong, we need to back up for just a moment and explain some broader terms. First, let's talk about what is AI. Artificial intelligence, or AI, is a term we hear all the time in news stories and often in data discussions, but it isn't always clear. AI is a term used to describe machines that have intelligence, a machine capable of solving a specific problem. Moving down from AI, we see that machine learning is a subset. Machine learning is a particular type of AI where the machine learns by itself, and the machine uses data to improve performance in learning. It's one of those fun terms in IT where the name is pretty descriptive, teaching a machine to learn. Moving on to neural networks, this is a system that mimics the human brain. Things go in, you learn from the learning. This may be repeated many times over, and you give an output. A simple neural network may have 3 layers, an input layer, a hidden layer, and an output layer. They also have some things that's called weight that connect everything and facilitate in learning. It's got some maths to it, but really that's the gist. Then we have deep learning. The deep in deep learning is referring to the depth of layers in a neural network, the how many times you are learning from the learning. A deep learning neural network will have more than one hidden layer. So it really has the capability to learn more and to learn from its own mistakes. Think of it like a toddler that touches a plug and gets a small shock. That toddler is probably going to conclude that plugs are bad, versus an adult that may have a much deeper understanding of electricity. The adult has learned a lot more along the way. So what is computer vision? Computer vision is largely a subset of artificial intelligence, and it gives a system the ability to potentially acquire, see, understand, and analyze image type input. Part of computer vision falls outside the AI group, as it also can involve things you wouldn't traditionally put under AI, like image manipulation. If I take a bunch of images and change them to grayscale, that's not really AI, but it may be an important part of the process of an image data set that I'm using in my computer vision project. So here's just a few different types of computer vision tasks. In the first picture, you see that every single pixel has been assigned a category. Green for grass, yellow for cat, pink for trees, and blue for sky. This is called semantic segmentation. If I had 3 cats in this image, they would all be yellow. That's why all the trees you see here are pink or lavender or whatever you want to call that color. The second image is 2 things. It identifies where the object is and it classifies it. So maybe in this instance, it would tell you that for this object, it puts the object as a cat at 90%, fox at 5%, squirrel at 3%, and a dog at 2%, something like that. In the third image, there are multiple objects. So kind of the same thing as the second image, but having to identify multiple things and sometimes multiple objects of the same thing, like the 2 dogs here. In the last image, you are identifying exactly where the object is and putting a mask on it to identify each pixel in the mask. Some similarities as a semantic segmentation. I could have also labeled the entire image like you see in picture 1. The difference is that each object is its own thing, even if the category is the same. There are other tasks, but this gives a good starting point. A project may just use one of these or multiple if it was comparing to see which one is better. In my project, I use semantic segmentation, but I could have used instant segmentation, and that would have made for an interesting comparison. Some key terms. I'm going to front load you here with a bunch of key terms that I used in my computer vision project, and will be relevant in just a bit, so bear with me, I know it's a lot. Key term 1 is in the center here, and we will refer to this as annotation. It's about manually identifying each object. Oh, went back. There we go. It's about manually identifying each object in an image and labeling it accordingly. The image you see here was annotated with an open source product that lets you manually draw edges around an object and then label each object. And later on, I'll show you a quick demo on it. In this image, you see roughly 17 objects that were identified and labeled. Then, depending on how you made these annotations, you can create outputs that a computer vision system can use to understand the image's content. Key term 2 is called ground truth. A ground truth image is often the output of an annotation process. In the context of a ground truth image, it is used as a mirror image to the original system to let it know what is what. That labeling you did in the annotation process now becomes its own image. Imagine a system going pixel by pixel between an original image and a ground truth image and learning by comparisons. Pixel 1 in this image looks like this. Pixel 1 in the ground truth is black in his background. Got it. Move to pixel 2. While this would be an incredibly slow process for a person, obviously a computer can do this a lot faster, and it learns the different subtleties of each pixel. I'm using pixel here as an example, which I'll do a lot in this presentation, but there are other ways to do this as well. Key term 3 is a much simpler concept, and frankly, it's not always used, but it's a really good thing to know, and that is a contour. A contour is simply drawing the edges around an object. It is the contour of the object. You can get this information in multiple ways. And if you look at my GitHub later, you'll see an example of how to build a contour image like this from a JSON annotation output example. And contours are common in computer vision, but you won't always have to produce an image like what you see here. When you do, it can sometimes be kind of tricky to produce it. So knowing the concept and the term is really helpful. Splitting a data set is another important concept in machine learning, and really in a lot of different statistical applications. The basis of it is that you want to keep a different set to train on, to test on, and to validate against. By doing this, you keep each set independent. That way, too, you aren't giving cheat sheets to the model. You start with one set of images, and then you typically split them into 3 sets: training, validation, and testing. Some people only do 2, and there are other methods as well, but knowing what we're talking about here will help as you run into these other scenarios. Your training is usually your largest set. This is what your model trains on. Your validation set is used to see how well your training set learned, and then you can tweak some parameters to see if it helps in the learning process. You want to make sure you don't overfit the model, though. What that basically means is that you want your model to be able to generalize and not just fit data exactly to the information you have given it. So what do I mean by generalize? For example, if I want my system to learn what a dog is, and I give it pictures of St. Bernards, Rottweilers, and Mastiffs, if I tune my model too much to these dogs, then it may miss the adorable Minkin I give it in the final testing phase. That's basically the concept of overfitting, only knowing the big dogs. Generalize is being able to make the information from the big dogs and abstract that to all dogs that may look different. Your last set, test set, is the most important one. This is the pictures you have kept completely separate, which you should have done for all sets. After testing with your training set against your validation set, you want that third set that has not seen the light of day, so you know how good it really is. Maybe your model was tuned too well, where it worked really well for your validation set, those big dogs, but not for any other set in the world. That final testing set will generally bear this information out. The test set gives an unbiased estimate of the skill of the final tuned model. Along those same lines, you typically will split your train, test, validate sets in percentages. You want the bulk of your data to be part of your training set. So giving higher percentages than the other sets, and then the remaining data going to your validation and test sets. Here are some typical splits of sets. Now, it doesn't have to be exact, and there are some pragmatic ways you can do it, but these splits are pretty common. For an 80-10-10 split, that means 80% of your images are going to the training set, 10% to validation, and 10 to test. You could also do numbers such as 75, 15, 10, with the idea you're trying to end up with 100%. In a lot of cases in computer vision, unless you just have gobs of images, 60% is not going to be enough to train. Conversely, if you're working with a small data set and you don't have an option to get more, then you should consider leaning towards the 80% split. You have to play around with it a bit. Ultimately, if you don't have enough images, you're just not going to get great results. And unfortunately, there's no magic number. It really depends on what your model is trying to do. So last key terms before we jump into the fun. When I did my first computer vision project, I remembered the concept of an image having what's called channels. I remembered at a basic level the concept of channels with RGB or black and white, but not really beyond that. In computer vision terms, an image is an array that has at least a width and a height dimension, but often has at least one more dimension, such as RGB color. I'm going to use the example of RGB channels here, but know that you're not limited to just that option. An image can have multiple channels that can mean different things. If we had a 5x5 RGB color image, then the shape of this image would be 5, 5, 3. In this example, the 3 represents a color dimension that gives a numerical representation for red, green, and 1 for blue, for the size and width and height. So our 5x5 image has a 3x3 square inside it with a red value of 255, a green value of 5, and a blue value of 100. The square at the bottom you see here is a smaller scale of what this would look like as an image. The zeros you see at the top of all the channels when combined equals the color black, 0, 0, 0. And 255 for red, 5 for green, and 100 for blue equals a fuchsia type color, the square you see in the middle. There are other types of color channels you can use, but this gives you the general idea. The WHC you see below the 553 shape stands for width, height, and color. Channels is a really important topic in computer vision that could be its own presentation. So if you're interested in computer vision, take some time to explore the different ways channels can be used. My project, what was it? Why did I want to do it? What we'll be walking through here is a project that I've done a couple times in different variations. Here I'll be talking about my capstone project because then I really don't have to worry about non-disclosures. And really, it was the project that I had a lot of gotchas and I feel could be most helpful to others. First, what was it? The official title was Computer Vision and Using Edge Detection as a Fourth Channel. What does it mean by fourth channel? Going back to what we previously talked about, that 3-3 representation, that 3-channel representing a shape of 553. And now we're going to add that contour image we talked about, which has a shape of 5-5, which is also known as 551, with the numbers being 0 or 1 in that last box to represent the edge. So we're going to concatenate that contour image with the original image, which in our example would result in a shape now of 554. Why did I want to do it? To see if adding the contour would improve results for identifying blood cells, particularly overlapping blood cells. Overlapping objects that have similarities is an ongoing problem in computer vision that doesn't have a silver bullet solution yet. By using blood cells, the ideas, code, and learning models could be used in other industries. A second part of the project was to be able to accomplish the various steps with low-cost solutions so that stakeholders in global health worldwide may be able to use part or whole of the project without running into significant costs. Given I had a hard deadline for my project, I needed to determine the steps I could take and then decide which were required, which were nice, and which brought value given the expected effort. Note, I had done a similar project before with a small team for a client, so I wasn't going in completely blind. This brought me to a 3-stage process. I personally like to divide them into these 3 categories: data, model, results. Notice the double-sided arrow at the bottom. That really signifies that these things aren't done linearly. Obviously, you wouldn't start with results, but after getting results or even while running your models, you may have to jump back to getting new data or going back and forth, which has happened to me many times. The first step was acquiring the data. You can't really do anything until that's in place. The primary data set I used is a subset of the microscopic peripheral blood cell images made publicly available. That means you can get them too, through the collaboration of the Clinic Hospital of Barcelona, the Technical University of Catalonia, and the University del Rosero Bogota. This set has over 17,000 images. I used much less. Images were obtained at the core laboratory of the Hospital of Barcelona and consist of red blood cells, white blood cells, and platelets. The images were annotated by expert clinical pathologists and organized into 8 groups. The class IDs 2 through 9 in this table are the classes that were identified in the original data set. The other classes, background, RBC, and RBCOL, are ones I added because my project wasn't trying to identify a single cell, but rather all objects within an image. The majority of the images were sized at 360 width by 363 height. This description file stated all of the images were of this size, But I later found out that there was a small number that were a different size. So before we even get into problem number one, I'll say first, do some verification steps on your data. Don't automatically go by what the documentation says or even what anybody else says. You definitely want to verify something as crucial in computer vision as size, because a lot of times you're going to need all your images to be of the same size. The original information with the data set stated that the data was annotated. My experience with annotated images came from the open source project VGG Image Annotator, also known as VIA, which you see here. It's a simple program that opens up in your favorite web browser, and you don't have to install anything. You can see the outside lines of each object, which is referred to as polygons. So if I was annotating something from scratch, flip here. Can you see that?
Yes, we can.
Okay. So if I was annotating something from scratch, I just kind of click around this, boom, boom, boom. It's not great annotation, but you get the idea. And since I made this all yucky, I can move some of these out. And then I assign it to one of the categories that I've pre-created. So by doing that, you go through and annotate each one of the objects you see. And then you can export these into various formats. So here you could do it as CSV, as JSON, as COCO format, which is also a JSON. Quick look here at what that JSON would look like, just so it gives you kind of an idea of what's under the covers. So here's what that actual image produced. And it gives you, because you could have chosen many different things with polygons or the other shapes. We used polygons here. I needed that for a specific reason, but it gives you all your X and Y points of each of those contours. So for each one of those objects, this file says, hey, this image has all these 17 polygon shapes, and then it gives you the XY coordinates of each little dot that I did, and then what category it belongs to. So here, this is the one that we did. We assigned it to RBC, and yes, it is an RBC, red blood cell. I just want to go straight back to that. Sorry, I have not refined my flipping between stuff. Right, let's just do this. Oh, it went straight back. Great. Okay, so that's what I expected. The annotations included with the data set. Some sort of file that I could pull into VIA, maybe tweak it a bit, and then poof, all my polygons would appear, and I could export my required VIA JSON file. I needed that JSON file format specifically for my downstream process that created those contour images we discussed earlier. This is what I got, a directory structure, with each image placed in one of 8 folders that was determined by the largest dyed cell in the image. For example, this folder contains all the images where the basophils were front and center. No identifying file that told me the X and Y points defining the polygon of the basophil or anything else in that image. Nothing, just folders and images. So I had to go back and start annotating each object by hand. I think my first 10 images took me about 45 minutes for each image. Clearly that was not going to work. And my 17,000 image data set was not going to be that big if that was my rate per image. I then got to delve into the wonderful world of annotation software looking for a faster solution. I had a second problem, and that was I needed to be able to create ground truth images. Somehow I either forgot that this was needed or assumed it was included or could be easily generated, but the final result was I didn't have them. So I needed three things ultimately from a second annotation application. One, quickly generate annotations on the image. Generate output that was compatible with the VIA import because of the downstream processes already developed that depended on that export. And three, generate ground truth images. I installed program after program. I even reached out to a couple of paid programs for student discounts, which they graciously gave me for a period. I installed Docker and got to learn and debug issues with that. Many programs that I tested had additional add-ons that you had to install to get even close to what I needed. I even tried a couple times to pragmatically make a solution that I could use with one of these programs, but it was not happening. I was going down an entirely different rabbit hole that should have been its own capstone project. It took me about 2 to 3 weeks of learning, testing, and debugging various solutions to get to my annotation requirements. Ultimately, I was able to find my software, though I still had to write some code for things related. But the big takeaway was that there's not one standard definition of what annotation is, and many of the different outputs from the various annotation software products are not compatible with each other at all. So if there's a downstream process that has any sort of dependency, you really need to make sure that you account for that. Now, almost 8 weeks into my project, I was still only in the data prep cleaning phase and my clock was running out. With the new software, I was able to take my 45 minutes per image to about 5 to 8 minutes per image. And it made the ground annotations and the ground truth images that I needed. Given the time spent on all these activities, my buffer for my project was greatly reduced, as was my data set. At some point, I realized I just needed to move on to the next phase with what I have and circle back if needed. I still had not created the contour images or tested these images in my networks. What was the final number of the base set of annotated images? 114. It seemed small, but I had worked on other non-computer vision classification projects, and in my sleep-deprived mind, it wasn't terrible. I was finding it difficult to find information on what was a good number for a computer vision project, so 114 it was. The software I used made ground truth images that I needed, and it produced an export of the annotations that was compatible with VIA. So I could then import into VIA and then export to my needed JSON files. For the contour images, I still had to create. The VIA export was pretty essential to creating those contour images. Thankfully, the code I had previously created to make contour images only needed minor tweaks. Finally, something was going right, so I could move on into the testing my now cleaned and completed data set with my previously tested neural networks. I'm going to get messy for a minute, and I promise to keep it short and high level because this really isn't a deep dive into neural networks. I'm not going to go into all the nitty-gritty details of the various networks, but I want to explain quickly a few things. This is the SegNet architecture I used. You take an image and its matching ground truth image, and this is what the network uses to learn. It takes those images, gets some important details, makes them smaller, repeats this process, and then makes them larger again to use in the prediction. I used SegNet because it's been around since 2016, 2017. It's stable, it's light, and it only has a few parameters you need to tweak during the process. It's memory efficient and comparatively easy to train. Also, I used it in a similar model, so I wanted to minimize debugging something different. My goal wasn't to find the best network, it was to see if using a fourth channel made an improvement. So in that respect, using an older neural network met my criteria fine. And yes, 2016 is a much older network. This is the edge detection network that I used. It's called Holistically-Nested Edge Detection, or HED for short. It's even older than SegNet, going all the way back to 2015. Again, not going to go into the nitty-gritty here. You can read the official papers on it, but I'll give you a high-level overview. For this network, you need your original image and its corresponding contour image. Remember that image that was generated from those pesky JSON annotation files in that downstream process I kept mentioning? In this instance, the contour image is the network's ground truth image, because all it really cares about is edges. In this network, there are predictions made through each step of the process, 5 total here, and then they're fused together for a final prediction. Like the contour image, the predicted image is really just composed of a one-dimensional array of 0 and 1s, representing if there is an edge or not. This prediction is the basis of the 4th channel used in the integrated network. And finally, our integrated network. We take the input image and the edge image, concatenate them together to make our 4th channel image. Then that concatenated 4th channel image is fed through the SegNet again with the original ground truth and results in a final prediction. I had already done this before and done pre-test at the beginning of the project, so I was pretty confident that all I would have to do is sit back and let the networks run. Problem 2, neural networks are not plug and play. Well, let me clarify that. SegNet was not plug and play. I was getting errors all over the place. I wasn't even to the point of testing my HED network or the integrated network. I half abandoned SegNet and tried with UNet, but it was giving me similar problems. I had used this setup before with images of a different size. My pre-test involved images and ground truth images that were the same size that I had previously used when running a similar project, and they had worked fine. So that was my first clue. One of the biggest changes from my pre-test was image size. That's where I started my investigation. For those of you that have coded for a while, most of you are probably aware of the poor person's debug tool called print. I used 2 images and printed out changes of the array size as it went through SegNet. Thank goodness for print. What I failed to mention before when I talked about this network is that when you start with an image shape and make it smaller and then bigger again, you want the corresponding shapes to match. Each stage that gets smaller needs to match its corresponding larger size. That image size we talked about at the beginning, 360 width by 363, yeah, the math did not work. They were not adding up. That 360 by 363 divided going down and then multiplied going back up didn't come back to 360 by 363. Even when I played with some padding parameters, you can change in SegNet. So now, knowing my images size didn't work, I had to find sizes that did work. There was no instruction manual with these things. Wanting to preserve image detail, I first tried tweaking parameters. That was a no-go. Then I sat with a calculator and paper to try to see what image size would work. After testing different sizes with changes in variables, oddly enough, it was determined that 361 width by 363 height was the ideal size that would minimize changes to the original images and still process through the network. If I had made it much bigger, I could have fundamentally changed the image. Also, our images were already kind of small, so if I made it much smaller, I could lose valuable information or cause other unintended consequences. So a helper Python file was developed, and what it did was copy the edges, the pixels along one edge, just duplicating it. This made the images run smoothly and resulted in no information loss to the images. What it also meant was that I had to apply this to all images, all ground truth images, rerun the annotation process, and then recreate the contour images. It's not a super lengthy process, but just remembering what is this effect. And if you forget something, you're going to find out more obtuse error messages along the way when you run it again. Once this was all resolved, I thought, finally, but my network still wasn't happy. It was giving me some more problems with channel size. Not my great edge 4th channel, because we hadn't gotten there yet, but a different channel. Turns out it meant a completely different thing. You see, not all ground truth images are the same either. First off, ground truth images are not all the same format. PNG and TIFF are frequent formats because they allow for transparency, but the underlying arrays can also be different. The ground truth images that have been created by the annotation software I used produced an image shape of 363, 360, 4. 4 instead of 3 because of the transparency layer. One of my error messages actually had value and said something along the lines of expecting 5 channels and received 254. I pulled the image into Visual Studio so I could use Python and look at the underlying array. 360, 363, 4. Was it having a problem with the transparency layer? Yes, but there was more. I pulled in one of the ground truth images that I ran out my pretest into Visual Studio and saw something interesting. Going back to our 5x5 image example, instead of the image shape of 553, in our case with the transparency layer 554, what I saw with the already tested images, ground truth images, was an array of 55 or 551, same thing. And this reminded me when I was trying to look at the MATLAB ground truth images I had created during my annotation software exploration. And I remembered realizing that the numbers represented in the 5-5 shape, like the 2's at the bottom, in the bottom box here, instead of equaling a combination of colors, it was representing the actual class it belonged to. So I went back and verified that every combination of numbers where the shape had that third axis translated into a specific class. It did. So I wondered out loud, can I just flatten this out, change the shape and replace with a class number for each combination? Turns out the answer is yes. By flattening the 3 blocks you see at the top to the 1 block you see at the bottom, the array has a singular number representing each block in the 3x3 square. In this process, the square's number is set to have a class label of 2, and the shape of the array changes to 5-5, which is what my network was looking for. By flattening out my ground truth images to the shape of 363, 361, a singular value was given to denote the class of each object with one of the 11 class labels I was using. Note, this is not the same as contour image we were talking about earlier. I'm changing this top row that has the last axis as a 3, that what we call channels, to 1 channel that you see at the bottom. And this was because my project needed the ground truth images to have the lower shape instead of the one at the top. New lesson learned for problem 3. Know the requirements of your ground truth images for your project. By the way, if you ever have to do this for a computer vision project, which wouldn't be surprising, if you try to open your newly saved image up in traditional image software, your image may end up looking something like this. Don't panic. Regular image viewers really just want to look at it like it's a color, and that black value of 0 is just too close to our class numbers 1 through 11. If you want to see what it looks like, then pull it into MATLAB, verify that everything you've created looks correct. Pull it into MATLAB or Python using a MATLAB library or some similar project. Then it'll go back to looking like you expected. Maybe not the exact colors you expected, but different colors for different channels. The colors are really just for your human eye benefit. Finally, we could run our images through our networks and get some results. Before we go into the results, I want to step back now and talk about those splits from the beginning. Recall we had 114 images, and we also needed to split those into different sets. Looking at those original splits and accounting for decimals, this is really what the splits broke down to. If you're fast at math, you have probably already noticed that line 1 isn't exactly right, but the decimals in this situation made the splits a little wonky, so we kept the splits as close as we could. Now, not every image has every object class. In fact, most images have 4 to 5 classes in it, if you recall from that ground truth image, which is why you would see about 4 to 5 colors. All of them had some classes, background, and the 2 classes for red blood cells was in every image. Sometimes they had even those tiny platelets, those tiny purple things we saw, and then usually one of the 7 other classes listed as 2 through 8 here. So really those numbers for splits started to look abysmal. In fact, that really meant some classes may be represented in only 2 images of the splits. That certainly wouldn't be enough to train on, and then not much better for being on your test or validation side. But let's hold that thought for a minute. What I realized right away was that from a training perspective, 60-20-20 was not going to be helpful, just too low of a number to even consider for training sets. Each split I used had to be run through each network, which is time consuming. I hadn't tested everything from end to end with evaluation metrics, so using reasonable judgment to cut one of these made it easier for me, and there was no use to keeping the 60-20-20 at this point. And these were my initial results. Very unexpected. My loss wasn't bad and my accuracy was nothing to sneeze at. Accuracy in the mid 80%. Accuracy is used here to let me know how often my model's prediction for a pixel was right. Loss just helps you to understand how much the prediction value differ from the actual value. If the model's prediction is perfect, then the loss is 0. Otherwise, the loss is greater. It's not like accuracy where you cap out at 100%, so your loss can actually exceed 1 or way more. If you look at the comparisons of splits here, my loss numbers was a little higher in my 70-15-15 split, so that means there was a little bit more error there. Looking at this first run of results, I thought, wow, I'm so amazing. I finally got this under control. This may be a good time to throw one of my favorite quotes in here. If you're not prepared to be wrong, you will never come up with anything original. And boy, was I wrong. What happened is that my classes were unbalanced. If you look at this ground truth image, what do you see most of? Black background. So my model got really good at learning and identifying background. What else do you see? A lot of orange and red, which represented single red blood cells and red blood cells that overlapped or were off the edge of the image. We also see those tiny purple platelets I was talking about earlier, and then one large basophil blood cell, which, by the way, as we said, was only in a small number of the images. Background and red blood cells are in every image, but not the other classes. So our model had fewer chances of learning the other classes, but got really good at learning the things that dominated each image and were in every image. Using accuracy as my metric wasn't going to work here. It was right 85% of the time because look how much of this image it could learn from each time. So I had to find a different metric. Using another metric called intersection over union, I was able to get a better picture of what was going on. It's an evaluation metric used to measure the accuracy of an object detector on a particular data set. With intersection over union, you use the ground truth mask and the prediction mask. Then you see how close those two masks overlap, aka intersect. If the masks overlap exactly, then they are the same as the union of the masks. So when divided, the intersection over union equals 1. If they don't overlap at all, then in this formula, it equals 0. Usually you have something in between. By using this metric, I could get a better idea of how each class fared. With this slide, I'm showing you what the correct metric was for my project. And you don't need to memorize this specific metric because really the big takeaway is that you need to make sure you are using the right metric for your project. And that's not exclusive to computer vision. Those of you in analytics have probably dealt with this before. Here's the breakdown of classes using intersection over union. Although again, not the same as accuracy, you can see how they have a strong influence on that original accuracy metric. By the way, the platelets had small examples like you see here, and then also larger examples in other images. So that's why you see a middle of the road results in the metrics here for the platelets. And this is the initial results with the two different splits. With our remaining classes, arguably the most important ones, we can see how dismal our predictions are. Even when you compare the different model splits, I don't think I had ever seen metric results so low. So what to do? I had 3 weeks left to finish my project, write a paper, and then afterwards have 1 week to make it all into a nice presentation for the capstone committee. Go big or go home. With no experience creating a synthetic data set, and we've already established that's okay with me, I decided that this would save me from all things horrible in my mind. Never mind, I could have probably closed the project with a simple, well, here's what I learned. I really wanted to see something with more meaning in my results, because the numbers I had so far were pretty meaningless and arguably could have changed dramatically when done in multiple runs. What I didn't know was that synthetic datasets that use real objects from other images to create new ones, showed a lot of promise in the field of computer vision. Fortunately, the rabbit hole for this one wasn't too bad. I stumbled on a website from Immersive Limit that led me to the author's GitHub page. I sprung for the few extra bucks for the corresponding Udemy course. I highly recommend it, by the way. I don't know this gentleman at all, other than me reaching out to him after I'd bought the course and asking a few questions. But if you're ever faced with having to create a synthetic data set on the fly, it's an amazing tutorial. And an additional bonus that went with it is that the author's code generated ground truth images and annotations automatically within the process. So I was all in. Now, I did run into some issues because, of course, his project wasn't exactly like mine. He used instance segmentation. If you recall, I used semantic segmentation. But the short of it was, after 1 to 2 weeks of flipping between that and working on my paper and getting ready, I was able to generate all that I needed. By combining it with my base set, I ran with a more balanced representation than I previously had used, although I used 0 red blood cells because of their density and my base set was so large. I created 1,800 images as a test and combined them with my original base set of 114. 1,800 was chosen because you do have to do some time-consuming masks of images that your synthetic data set generation process will use to create the new set. It will randomly choose those individual masks from a pool, make some changes to them, and then randomly put them on a background. The images that you see here are some of the actual images that were created in the generation process, which I thought was pretty cool. You'll probably never have a lab slide of cells that look like these combination, but it turns out that computer vision really doesn't care. It's just learning what those different objects can look like in different scenarios. You don't need fancy software to create this, just GIMP in a Python IDE like Visual Studio. So after that was done, the entire process was run again. While not ideal results, this was looking much better. And remember that our main goal was not to have the highest metric as possible. Our goal was to see if there was a notable difference when you added a 4th channel, good or bad. So while the results were still pretty low in some cases, what we do see is that there is significant movement with adding the 4th channel, especially for some reason with the neutrophil. And looking at our drastic drop in red blood cell classes, we also have learned a final lesson, and that class balance makes a difference within the individual images as well as across the entire set. So if you look at the intersection over union mean here, and even better yet, the adjusted mean, which I just did to test if I threw out the RBCs completely, you get a better idea of change between the networks. One of my final recommendations for this project was to increase the synthetic set by way more, which could be done reasonably within a couple of weeks on the side. That really wouldn't make my timeline, but I had my answer that I could present and finalize in my very large paper that was coming due. So recap. Problem 1, know what you need with your annotations and know what you're getting. This includes knowing if there are any downstream processes, process dependencies. Problem 2, not all neural networks are plug and play. There is a big dependency on the actual images, and you need to know what those are in advance. Maybe it's size, maybe it's something specific with ground truth images, maybe it's something else. But knowing what these things may be can save you a lot of headaches. Problem 3, not all ground truth images are the same. This ties into problem 2, but take a moment to pull your ground truth images into Python and see what it is under the covers. 1, it's actually kind of cool to see, but 2, it gives you an idea of the shape and really thinking in the space of how the shape applies to other images. Problem 4, data splits. Choose the right split for how many images you have. This really may be better titled as make sure you have enough data. Computer vision needs a lot of data. There's not a specific number, but I can tell you 114 is not the right number. Ideally, you will have over 10,000, but again, it really depends on what you're doing. Some projects may require millions. Problem 5, and I found this holds true for a lot of machine learning tasks. Make sure you choose the right metric. If you're not sure, try different ones and do some background research on what the best metric is for the task you are doing. Some fun stuff now. Here's an example of a real image and prediction between the base network and the one with the 4th channel. They're pretty similar with the prediction on everything else. And the goal is to look as close to the ground truth as possible. I think that center one is a basophil. There we go. And you can see where it has more purple leanings in the edge detection network compared to the regular SegNet. And it's a little stronger also on the platelets. So something funny here I noticed when doing my paper, and I don't think I brought it up, but I may have. If you notice, the ground truth here is peach, is labeled as peach, and both predictions have it as cream. The ground truth is actually labeled wrong. It's just hitting that edge, and I should have labeled it as RVCOL, which is cream in color. And the models caught it. One of the often cited benefits of neural networks is that when a human labels things, they may make mistakes because of fatigue or other issues, which I certainly had. With a neural network, you don't really have that. This was kind of a real live example of that for me. And lastly, and mostly because I thought this was super cool, here's a comparison of how the networks learned on different iterations called epochs. At the beginning, the SegNet learning is super fuzzy compared to the integrated network. Okay. With some pretty immediate identification of objects. But then later, the integrated network, at least for this image, seems to have some issues in some places. I'll show you that. There. So that one is not, it's missing kind of this where it's transferring to blue, and it's really doing more of the whole thing. Although it does seem to do the platelets a lot better and identify those quickly, whereas here it's still trying to figure it out. So putting this presentation together reignited my desire to go back and explore this a little bit more and clean everything up for GitHub. And hopefully I'll have those. They're not all the way up because I do have to take some stuff out, remembering that some of the code I reused from other projects. So I got to make sure it's clean and I don't have any information in there that might get me in trouble. So hopefully I'll have those updates if you're interested looking in GitHub pretty soon. I expect about a week. So one of the biggest things I learned in my AI journey is that most projects are not groundbreaking successes, especially at the first or second go of a project. Whether that's at school or work or obsessive hobby, COVID people, you know who you are. Everyone wants to be on the cutting edge, but don't let that make you miss out the most important lesson. Does your project provide you with valuable information? Because that really is what the ultimate goal is. to the resources mentioned in this presentation. My paper is also available on my GitHub if you're interested in all the details, and I do mean all the details. And I think that kind of concludes everything, and we are ready for any questions.
Yeah!